this tutorial, we're going to simulate the flow in a replica, pilot scale, anaerobic digester using the MRF approach and the RBM or sliding mesh approach. So we're going to perform two simulations. One is a time averaged case, one is an instantaneous or transient case, and then we're going to compare the results at the end. So we're going to begin as usual by right-clicking on Geometry and opening Design Modeler. So this tutorial is going to talk us through developing a rotating domain within a stationary domain. And this is going to be in the shape of a cylinder replicating a pilot scale anaerobic digester of about 0.3 meters in diameter. So it's going to be rotating about the z-axis. So I'm just going to zoom in on the scale at the bottom to get us approximately in the right length scale. And because we want it to rotate about the z-axis, I'm going to be sketching on the xz plane. So just create a new sketch, make sure we select circle, and just select the point in the middle and drag it out to approximately 0.3 meters. We can dimension that up properly now, and we were not too far away. There you go, 0.3 meters. And we're going to extrude this sketch. I'm also going to extrude it in about 0.3 meters as well, so it's of a relatively similar size. Just make sure we've added material, make sure we're going normal, and then we should create what's going to be our outer domain. So inside what's going to be our tank of water is going to be another region. That's going to contain an impeller, and that's going to spin rather than having the impeller spin on a mesh and having to constantly rebuild the mesh. So I'm going to create another plane offset to about half the height. So create new plane, transform. If you right click there, you can select offset and global Z. So we know the total height is 0.3 meters. So we can set this at 0.15. And if we just right click and generate, we're going to begin by actually cutting a section out of this container. So if we just view from the top, we're going to cut out just bigger than the size of the rotating domain we want in the middle. So we're going to create another circle. And we want it to be about 0.2 meters. So again, just add dimensions. And what we're going to do now is we're going to extrude this in either direction. And we're going to basically cut away at the outer, what's going to be the stationary computational domain. So just select extrude, make sure it's sketch 2. Instead of add material, we want to cut material. Instead of normal, we're going to have both in symmetric. And this is going to be 2 centimeters in either direction, which will be a total of 4. Then we can generate that. And obviously you can't see anything here, so we can just run a section plane. Then you see that empty region there. We're then going to nearly entirely fill this up with another shape. So again, back to that offset XY plane. Create a new sketch this time. And what we're going to do is create a sketch, well, a sketch of a circle that's ever so slightly smaller than the original. So if you remember, the original was 0.2 meters. This one is going to be 0.1, let's call it 999. So it's close but not overlapping. And then we're going to fill that region, again, not completely, but almost just leaving that slight offset. So we're going to extrude, select sketch 3, we're going to add material. Like we did with the cutting, we're going to do it in both directions. And just make sure we set it as, again, not completely filling, but very, very close to. Okay, let's just check we've done that right. Sketch 3, both symmetric, fixed, and a similar depth. Cool, so we can generate that, and just to confirm that we're right, you can see there's two different regions here. The outer stationary and the inner moving. So one more thing we need to do now is actually create our impeller. So I'm going to do one final sketch. This time it's not going to be a circle. Just going to zoom in here slightly. Going to create a sketch on the same plane, the plane 4. This time we're going to model some really simple impeller blades, just using some rectangles, and we're going to nearly entirely fill the rotating region just to make sure that we actually get some movement of fluid flow. So we can add some dimensions to get some idea of what's going on. So our region is 20 centimeters just under in diameter, so we can make that 0.18. And if we make it 2 centimeters in width, I just use the various dimensions to centralize about the axes. Just because it says vertical doesn't mean it's vertical the way you look. So if vertical doesn't work, do try horizontal. Sorry, that one needs switching, so in that case we need to use horizontal for what appears to be the vertical. Okay, so that needs to be 0.1 because it's 20. Sorry, it needs to be 0.09 because it's 0.18 total length, and then that one needs to be 0.01 because it's 2 centimeters. And then what we're going to do is just create the exact same shape in the opposite direction. So again, rectangle, and just break out your dimensions. Sorry, got that one wrong. Okay, there you go. So we know that needs to be 0.01. And that needs to be 0.02. That one needs to be 0.18. And that one needs to be 0.09. There you go. So we're going to extrude this sketch in a minute, but what we need to do first is just break off these edges that are currently in the middle. So we can just use that using trim. So in the gaps between either an axis or the outer of the shape, just click once, and it'll just remove those kind of, I'm going to call them filling edges, but edges that sit within the middle of the shape. Right. If you remember, our rotating domain is 4 centimeters in the vertical. So what I'm going to do is extrude this sketch using the cut function, but I'm going to do it as 0.01 meter in either direction. So that gives us 2 centimeter total height. And instead of adding material, we'll be cutting. If you do get these wrong, there's no harm in just going back and changing the extrude. You can do it for the most part as long as you haven't massively affected other things. Okay, just try this. There you go. So you can see our cuts there, and then if we do a section plane in the other direction, it's probably a little bit easier to view. Just turn off that section plane 1. There you go. So that's the computational domains that we're working with. I'm just going to label them for later on. So this, as you can see, is going to be our rotating. And you can also tell because there's so many faces on it, they've obviously all come from the impeller region there. Cool. So when you're happy, just save that and close it down. So in our meshing software, what we're going to do is first of all mesh our impeller. So I'm just going to use the F8 key to hide these other faces. Or you can just right click and select them manually. It's a bit tedious to do it this way, but it's not the end of the world. Okay. Can just view that from the side there. So I'm going to begin by setting a 2mm mesh size on these faces, and I'm just going to use box select for that. I'm relatively constrained with computational power on this machine, so I am just going to put a general domain wide sizing of 1 centimeter and just hit mesh on that. What you'd also want to do, if you did have more resource, is mesh the walls that join the rotating domain with the stationary one. This just help the gradients when it's solving, because if you have too larger cells, you're not going to be able to capture those gradients properly. I know there's some interpolation going on, but it's not going to be as effective. There you go. So you can see how very localized smaller cells in that region there. We probably could get away with some more, but okay, probably could get away with some more, but I'm going to leave it for the moment and just demonstrate the principle. Then you can obviously come back and refine that if you have more power in your PC. So just closing that, right click update, and then when you're ready, open up the Setup CFX. So you can see our computational domain here. Well, actually our 2 computational domains with the interfaces. But we'll also notice the fact that we've only got 1 default domain. Okay, so we're going to create a new domain and call it rotating. We can pick it from our list here, and you see it's highlighted, therefore it's the one we want to use. I'm going to create a new fluid and call it water, and select the water option here, which will have the correct thermophysical and transport properties. We know it's a rotating domain, and we can specify it as rotating, I don't know, let's say 2 revolutions per second, although if you want to use radians per second or revolutions per minute, that's also fine. And we can hit apply there. We'll notice we're getting some resistance, and we'll come back and address these shortly. So we have our stationary domain. This beginning section is going to be a moving reference frame where we're effectively telling the solver that this is moving, but it doesn't physically rotate. Later on, we'll have a look at what you call rigid body motion, where the object does physically rotate, and we'll end up stirring the flow that way. So because we have two separate domains, they need to talk to each other and pass information about the fluid flow across, and that's dealt with here in interfaces. The warning we're getting down here is about this particular option here, and we just want to choose a frozen rotor stator option. So this is just replicating or rehashing the fact that we've got an MRF system going on here. Right, the setup's relatively straightforward. We can do the usual things like force, the local timescale factor. It's a relatively simple flow as far as they go, so it should give us reasonable convergence within about 100 iterations. I'm going to initialize this for when we end up using it for an instantaneous simulation later on. So just specifying our initial velocities and pressures. And I'll just drop that turbulence intensity there. Okay, so just give that a save, and when you're ready, close it down and open up Solver Manager. Okay, so we're beginning to see the residuals drop pretty heavily. Obviously, they're going to hit some level of convergence. It's not going to be fantastic with this setup because it's a relatively coarsely setup simulation. When we're having looking at convergence, we can actually look at forces and moments. So this here is going to be the boundary condition for the surface of the impeller. So it's the rotating domain default surface. So if we just select OK there, we're effectively looking at the torque on it, and you see that's nowhere near reaching an asymptote. So we're still increasing in the negative direction pretty consistently. So as that begins to level off, that will indicate that we're getting towards convergence. Okay, so at about 8 iterations, we've got some pretty rapid convergence on that torque. And just seeing how that reflects in the residuals, we've just kind of gone through a plateau at about 10 to the minus 2. And then we seem to be decreasing further. Obviously, this is RANs and not a particularly well put together simulation, let's say. I've not taken much effort to make sure the cell qualities are fine. So I think we're doing all right there. Okay, so I'm going to stop that before it goes any further. I'm happy that we've got some kind of convergence, albeit relatively weak. So once this finishes, we're going to have a little look at the results. So there's the outline for our domain. So I'm going to plot some planes first of all in X, Z, and then Y, Z. So I'm going to show you something here. So we'll just use velocity for the moment. And we'll say maximum of 1 meter per second. And then what you'll see is really high velocity within the rotating domain, and then relatively limited outside. So what we can do is use another variable that's called velocity in the stationary frame. So it's going to be velocity magnitude in the stationary frame. Obviously we have the UVW components, and that will then give us a more relative to the stationary frame, so in this case the non-rotating domain. So you can see where our local peaks are in that. You can also plot some streamlines. Before I do streamlines, I'll just do that second and third plane. So this one's currently in XZ, so I'll do YZ again at the center line, and then finally another one at the center point in the domain, which is XY, and you can always drag this up manually, or just put it as 0.15 meters. Cool. So again, just following the colouring practices that we did in the other case. There you go. So you can see a lot of the actions going on in this, obviously between the blades, as you'd expect. You can use streamlines. People normally use streamlines to visualize this kind of thing, either on the planes or in 3 dimensions. So first of all, just plot it on the surfaces, planes 1 to 3. I think we use about 250, put them equally sampled, put them in the stationary frame, make them forward and backwards. Let's see how they look. And we could even just turn these planes off for a second to see how it appears. Might be pretty difficult to read, but yeah, you can see we've got a symmetric domain. We've got 2 kind of planar sets of vortices about the outward edge, which again you'd expect that. You'd expect some biasing if you had it taller in this region. And you can obviously see that the highest velocity regions are closest to the outside of the blades, which again, that's where the highest velocity surface is. Cool, no surprises there. Okay, so what I'm going to do is shut this down, keep that as it is. I'm actually going to rename this one and call it MRF for moving reference frame, and then I'm going to duplicate it. So now we're going to perform the RBM simulation. So this is where we actually move the domain, or move the rotating domain. So we can keep the mesh the same. I'm just going to change the setup slightly. So before, when it said steady state, we're going to change that to transient. Total time of about 10 seconds, let's say. I'm going to keep the time steps constant. I'm just going to want to make note of some of these numbers here. So we've got a total time of 10. We want to give it some time to spin up. And then we're going to start taking averages about halfway through. So that'll be about the 100th time step, 5 seconds. And then we'll average from the 100th time step. So we can OK that. What else do we need to do? We need to make sure we've got some transient results out. So in output control here, I don't actually want the transient results. What I do want is the transient statistics. So transient results will give you intermediate files where you can create an animation from them. I'm not actually that interested. What I'm interested in is getting time averages of values. So we'll get our velocity and velocity in the stationary frame. We'll perform averages of them. So we're going to start at, as we said, there's 200 time steps in total. So if we start at 100, and then we finish averaging at 200, it's not particularly clear here, this start and stop iteration list. Okay, this is going to be quite a significant simulation. I think I've run this something similar before and it took about 3 hours. So what I'm going to do is set this off and then come and pick it up tomorrow evening. So again, just refresh. And then I'll just check if it needs anything else, but it should be okay just to run. Okay, so our instantaneous simulation is finished. So there's a few things to note. So first of all, we've generally got a Courant number in the order of 10. What we're looking for really is a number about 1. So simple resolution really, rerun it and divide the time step by 10. Obviously, as this is a demonstration, I'm not going to bother doing that. But you can if you really want. The other thing to note, of course, is this change in torque here. We'd always expect an initial startup transient. And we've got 2 revolutions per second, and it's run for 10 seconds, so there's 20 basically revolutions that's being mimicked here. What we're seeing actually, we're getting towards an asymptotic value as we reach the end of the simulation. So if I were to rerun this, I would be very likely to maybe double or triple the length of the time and then begin the averaging, again towards the end of that. So we started averaging about halfway, so we should see an average torque in the order of minus 0.08 Newton meters. So yeah, just some interesting findings there. So hopefully you'll recognize the kind of, let's say, reflected sets of vortices above and below that horizontal plane. What you'll also notice here is we've got some very inconsistent, unsymmetric elements in this vertical plane here. Actually, unsymmetric about both kind of symmetry planes. And again, that's to be expected when we've got a instantaneous simulation that hasn't properly had time to time average. So again, like I said before, simple resolution really. Go back, decrease the size of the time steps and increase the number of them in order to get a very decent average from this. But yeah, just wanted to demonstrate those 2 different approaches to solve the same fluid flow. If you have any recommendations for videos you'd like to see, please let me know. And if you need any help, feel free to contact me via the channel information page.